So my name is Don Wibbles. I'm the chair of the Global Environmental Change Focus Group, and I want to welcome you to the Stephen Schneider special lecture that we now have approved for, we will be giving this at AGU every year. We still need to go through one more process in order to be able to hand out a plaque with it. So all I have for Warren today is a certificate, but from now on we hope to have a plaque as well. It's really my pleasure to have my old friend, hope he's willing to accept me as being his friend, Warren Washington as our special speaker. Warren's one of my favorite people. He's a great scientist and also a real gentleman. And it's really great to have him here. I could spend a long time talking about Warren's many accomplishments and his many awards. I'm just going to highlight just a couple of things. Of course, he's a senior scientist at the National Center for Atmospheric Research at NCAR. He was one of the first developers of global-scale climate models, starting when he came to NCAR in the early 1960s. He must have been a teenager at that time. I don't know how he could be where he's at otherwise. Actually, he was also the second African American to get a doctorate in atmospheric sciences in the U.S., as far as I understand. Member of the National Academy of Engineering, a number of different fellows in a number of different organizations, but unfortunately not AGU. We need to get him nominated, please, somebody. I might do it myself if I could. He has been a member and leader of the National Science Board for a number of years. He won the 2009 National Medal of Science for his fundamental contributions to the understanding of the Earth's coupled climate system, his leadership in U.S. science policy, and inspiring mentorship of young people of all backgrounds and origins. And his most recent thing, he's just telling me about it, is that the public broadcasting system has a show called a Night with Warren Washington that is making the rounds through the U.S. We haven't seen it yet in the Midwest, but I'm looking forward to that. So let me welcome Warren up to the stage and turn it over to him. And meanwhile, I will also provide him with this special certificate. Thank you. So it's all yours.
Okay, thank you very much.
Let's see if I can start this timer.
I thank you, Don, for introducing me. It's really a pleasure for me to give this talk. It's going to be kind of a one-person definition of where I think this field has been and where it's going. I'm going to talk about some new things that are challenging for us to sort of make progress in this field of climate modeling or system modeling. So I think if everything works right here. I'll give you a very brief history of climate modeling and Earth system modeling and some predictions of the 20th and 21st century and their effect on society. I'll talk a little bit about the Global Change Research Program, which was established in 1990. And I might point out it was really set up by a Republican president, George Bush Sr. I'm not sure that the current Republican administration is so enamored with climate change, but it was really a far-sighted document when it was enacted by Congress. And I'll talk about the strategic goals, and then I'll say a little bit about Sandy and the influence that it's had on national policy. And then finally, I'm going to show a video of Steve Schneider talking about our role as scientists and what we have to do to help convince a reluctant public that this is a serious problem that has to be addressed. On the observational story, well, I think all of you have seen these kinds of graphs essentially showing that the carbon dioxide levels have been fairly low up until 50 years ago or so, and then they started rising. And if we carry out the largest CO2 and other greenhouse gas scenario we can actually be, at the end of this century, up to 2100 if we don't start doing more mitigation. And I think that on the lesson here is that we have not seen these sort of increases in the last 800,000 years. And I think that you've also seen a lot of these kinds of graphs showing carbon dioxide, methane, nitrous oxide, and CFCs increasing substantially. And the largest emitters, of course, have been the U.S. and Europe and so forth, but now China is on the largest emitter. And I'll talk a little bit about some new developments that are happening in Doha from the U.S. So there is some momentum towards the U.S. working with China to see if they can come up with the bilateral agreement to start to seriously curb greenhouse gas increase. I'm going to show two videos right now of, I think, that how future satellite technology can give insights on how the climate is changing. You know, typically we look at things like the monthly averages or the precipitation averaged over a certain period of time, but I think that we need to go further into trying to really look at the interaction in between greenhouse gases and changes in the environment. Here's a video generated by JPL scientists showing the AIRS instrument looking at the mid-troposphere carbon dioxide concentration. And you can see on the seesaw pattern from the Hawaiian station actually measuring on the breathing of the CO2 in and out. So I think in the future we can start doing some inner comparisons of our model and looking at not the long-term averages, but actually looking at the details of the intake and outgassing of CO2 as it interacts with the vegetation. And here I'll show a superimposed oops, I didn't quite take it. It's actually showing this over again. My next video is supposed to show the vegetation change too. Let me see if I can hit enter.
Is that what you want?
No, I think.
No.
Let me go do this.
Yeah.
And then. Oh, there it goes. Oops.
Past it.
Here, I'll do it. Sorry for the technical. Oh, okay, here we are looking at atmospheric carbon dioxide and vegetation. And you'll see that when the vegetation, for example, in the northern hemisphere starts to grow in March and April, that it takes some of the CO2 concentration out of the atmosphere. And then in the fall and winter, when the vegetation dies and essentially gives the carbon it actually allows for the carbon dioxide to come out of the vegetation that is decayed or dying and goes back into the atmosphere. And we haven't really tried to compare these kinds of things with on the models that have active carbon dioxide cycles. And so we're going to be getting more of these type of interactions that we need to use to help verify our climate and Earth system models. And here's a graph showing the land temperature averages globally. I just take special note of in the bottom right of the work of Richard Muller, who was formerly a skeptic. He wanted to repeat in a different way on the calculation of the land temperature change, how it changes. And you can see that it agrees very well with the GISS data, the Hadley Center data, and the NOAA Center. And so this was a project that a skeptic had actually tried to sort of do it differently and to show that the people who had been doing this were possibly doing it wrong. And I think what we found out of this study is that the old data sets and the old methods were pretty good. So this is another sort of nail in the coffin, so to speak, about on this land temperature change and the global average temperatures are real in terms of increases. And also another way to look at this is in terms of extremes. We can look at decadal heat waves and cold well, I won't say heat waves, but sort of heat and cold records. And as the decades have gone from the 1950s up till the present, that we're showing that we're getting more heat waves or heat records, and that this is actually proof on the climatological time scale that the planet's actually warming up. One of the things that is talked about a great deal is whether the solar variations are causing the climate change that we've seen quite recently. And as far as we can tell, even though this is the amount of solar energy coming from the sun, it does go through 11-year cycle, as is shown on the graph, but there doesn't seem to be any sizable trend. I might add, though, that in order to generate on this type of record, you have to do a great deal of removal of biases in the various instruments as the calibration changes. But anyway, this is the best estimate. So I think most climate scientists don't think that solar variation is a big factor in terms of the recent changes in the climate. Now, the climate and Earth system modeling, obviously, we've had for a long time, going back to on the original paper of Bjerknes, a articulation of the laws of physics, and now we have to work in the laws dealing with the biology. I won't go through the details of this, but if you look at what we have in our models, we have essentially all of these of the basic laws and the physical processes. And here we show a schematic of all these processes. Here again, I won't go through the details of this, but from the days in which I started climate modeling, which is in the early 1960s, everything was extremely simple. And the reason it was simple was the computers were so inadequate that it essentially took 1 day of calculation to simulate 1 day of simulation. So it was hard to make real progress in those early days. And we kept on the physics and on the dynamics and the resolution very low. And here I show kind of an evolution of the horizontal resolution, starting with the 4.5 or 5 degrees. And I show on the out of focus to a certain extent a smooth orographic of the showing on the mountains and so forth, and also the coastlines were kind of fuzzy because it didn't have on the resolution. And as we got into the into the present, that were used for the IPCC assessment, you can see that we've improved on the resolution of the models quite a bit, going up to a sort of 1 degree, and then going up to 1/10 of a degree. Here on we look at our most advanced in terms of high resolution models, and they do a pretty good job of representing orography and the ocean. And this couldn't have been made possible without enormous effort to make our models more efficient on the new types of parallel computer systems. I'll show this slide very, very generally. In the early days, we stuck to essentially a latitude-longitude grid, which gave lots of resolution up near the North Pole, more than we wanted. And we're going to sort of different configurations. One of the ones that seems to be gaining in popularity is a cube sphere, where you have more of a uniform grid structure over the entire globe, and you don't have an excessive amount of resolution up near the North Pole. Now, here's a timeline of climate models, and I'll just, I mentioned in the early days it was mostly just atmosphere, very simple land, and very simple ocean. And now, as you look at the far right of this figure, you see an atmosphere, land surface, ocean, sea ice, and a couple configurations, and we have sulfate aerosols, but we also have other aerosols such as black and brown carbon aerosols, a carbon cycle in some of the versions of the model, dust and sea spray, and interactive vegetation, and biochemical cycles, and ice sheets. The ice sheets are being introduced into our models as we speak. And now I should point out that even though we move up in the resolution, we still get substantial biases, and that requires us to still adjust some of the parameters, because on the parameterization for high resolution and a lower resolution models, even though it looks on paper as if you could scale it, it doesn't always scale, just because I think on the physics changes as we go to higher resolution. I'll show some examples of that. Here I'm going to show on 1/8 of a degree model that was run on a cube sphere. It's a work of Mark Taylor and many of his colleagues. And you'll see here, like in the Gulf, there was just a hurricane right there. We're looking at precipitable water. This is essentially the vertical integral of the vertical water vapor. And on the left, you will be seeing in the Pacific Ocean 2 hurricanes start to form, or typhoons for that part of the world. If you look off of in the tropics, you'll start to see two typhoons forming and these typhoons will start to merge and rotate around each other, which is often seen when you have two hurricanes or typhoons. And so we're getting out of such models when you go to very high resolution, very interesting and more detailed tropical simulations of tropical storms and hurricanes. Here I show a 1/10 of a degree model for the world's ocean. If you look off of the coast of the U.S., you see the Gulf Stream. It's actually shedding eddies on the Kurashio off of the coast of Japan, and around the southern part of South Africa, and we're getting eddies that they essentially go from the Indian Ocean into the South Atlantic. And around Antarctica, you'll see eddies there too. And so eddies are ubiquitous in very high resolution models, and we're able to execute models like this on our supercomputer systems, and there's some ongoing studies of coupled models in this sort of framework. But if you do this, you need to have a computer that has at least 100,000 processors, and you use a lot of time. But we're getting much more of the realistic simulations. And I expect in the next IPCC for the assessment of the CMIP that we'll be running models like this in the future. And the sea ice, and we're doing a better job of simulating on the sea ice in the Arctic. In black, you see the observations, and in the red, the sea ice extent from the model. And then we're doing a pretty good job of capturing on the year-to-year changes in the sea ice. So on that too has come a long ways. And here's on the velocities of glacier melt, and we're capturing on the major observations. And now this is a calculation of a standalone glacier model. But you can see at the 5-kilometer resolution of this model that we do a good job of capturing on the major glacier flows. And hopefully on this model will eventually be coupled to advanced climate models. In terms of El Nino, here I show an El Nino pattern, observations on the left and from the model on the right. And we get and underneath that you see on the El Nino is the red, and La Nina periods are on in the blue. And that we actually are able to show that we get roughly on the same frequency and amplitude of the El Nino and the La Nina events, and so that this is another indication that we're able to capture one of the main aspects of a sort of a regional forcing of the climate. Here I show a climate model genealogy for CMIP2, CMIP3, and CMIP5. I think the thing I want to show you is that in CMIP2 there was a big spread in between on the better and the worse models. Now as you go down to CMIP5, you see that there's less of a spread. It just means that we're getting on the models even though they do the physics in different ways, or the solving of the equations in different ways, that they're agreeing. And what we're comparing with here is the precipitation and the temperature on the surface temperature. Now, the other thing to sort of look at here is that when you go from CMEP 2 to CMEP 5, that all of the models are getting better in general. So that this means that we're probably able to give better and better advice to policymakers from our modeling studies. Okay, in the modeling of future climate, well, I want to say that mitigation versus adaptation. If we do nothing, it's all adaptation. I think that we obviously will need both to sort of solve this problem. For us climate scientists, we already know that we should be cutting back on emissions much more than we are at this point. And I think the models are capable even now of providing vital information on both climate change and its impacts. On the Copenhagen, Cancun, Durban, and Doha climate change conferences haven't really solved the fundamental problem of cutting back emissions. I already mentioned some new hope is starting to take shape at the Doha meeting from the U.S. as of just a few days ago. Now this is sort of where we are. You see in the lower left, we're still early in terms of the future scenarios. We are now carrying out these calculations to the year 2300. And the reason that we want to do that is that we want to also see on some of the longer scale features of climate change, for example, sea level rise. But there's only one of these new scenarios that requires a negative CO2 emissions, and that's the RCP 2.6. So someone will have to come up with a good way of taking CO2 out of the atmosphere to actually achieve that, and I think it's rather dubious. So I think everyone now is really concentrating on seeing if we can really even get to the 4.5, which is going to be a big thing to accomplish if we are able to sort of do it. And here I just want to show a shift in the anomalies. This is a distribution of northern hemisphere summer temperature anomalies. And what we really have done is change on that bell-shaped curve to a warmer climate already, and that's going to keep on going until we start to do something about the problem. I show a picture here of a child with a face drawn on it, and I wanted to emphasize here that it's really the next few generations that's going to deal with the aftermath of what we do right now. I think that you already know that this is not a problem that is going to probably be solved in our lifetime, but maybe we can make some big strides. And I think that that climate and Earth system models have and can continue to contribute to the understanding of the climate system and the predicting of the climate system. And out of our models, we can objectively determine possible impacts on climate change for food, flooding, drought, sea level rise, and health, as well as for decision support. Now, some of the lessons learned from Sandy, as you know, the cost of the repair for the infrastructure is roughly $60 billion and counting. 20 of the 30 the most expensive weather disasters years occurred after 2001, so we know that we're pushing on the system to a new sort of dangerous level, if I can say that. Most people in high-risk areas do not have insurance. They have the philosophy, it never happens to me, and 90% of the people in California do not even have earthquake insurance. Homeowners insurance only covers wind usually, and the cost has doubled and tripled very recently. So I think what this is telling us is that we cannot let people on their own decide to live in high-risk areas like on sandbars and things like that, that we need to kind of take into account that we have a changing climate and they can't keep doing the same things over and over again and expect somebody to pay for it. So the states have set up insurance plans because the private sector is moving out. For example, in Florida, but these plans are really underfunded. And people who live in low-risk areas are helping fund those in high-risk areas, and that's not a stable situation. And the national flood insurance is greatly underfunded, but Congress rightly increased on the rates, roughly 20 to 25% increases per year, and that's going to discourage people from living in the same places. And the government's already borrowed $18 billion from the Treasury for hurricane damages over the years 2005 to 2008. And most people canceled their residential insurance after a few years because they aren't required to keep it, only when they're buying a new house. And this is a terrible policy. I think people need to be self-insured as much as possible. Okay, now I want to tell you a little bit about the U.S. Global Change Program. The reason I know a little bit about this is that I chair the review and advisory committee for the academies as we review on the research agenda. It has a budget of roughly $2.7 billion, and most of you, or many of you, I should say, in the audience are getting funding from various agencies who are carrying out the research in dealing with climate change subjects. And I just show on the icons of many of the agencies. And the goals are to advance science, to improve our understanding, to study on the science of adaptation and mitigation, observations, modeling, and sharing information. And in order to carry out the first goal and the second goal, well, actually all the goals, and we're going to have to broaden ourselves and interact more strongly with social scientists and economic scientists. And I see that happening. And we're coming up with a situation where we'll be taking a new national climate assessment, and there will be people here who are very knowledgeable in that area. And there again, we're giving information to the public and to policymakers about how to adapt, how to mitigate, and prepare ourselves for a changed planet. Goal number 4 is to more effectively communicate what we know and don't know, and to educate on the public as well as policymakers. And then a final one is the development, the future scientific workforce to work on this area of science. Let me skip this one because it's a little bit detailed in terms of time. On the Obama administration announced just a couple of days ago it'll be working with China to develop international treaty effort to cut emissions for the greenhouse gases, and it was announced. What the U.S. will be doing is pushing for these cuts in the emissions by establishing rules for the vehicles, and that's already being done, new power plants, clean energy, renewables, and natural gas and nuclear. And I want to point out kind of one thing to remind you all. If we look at surveys of the public trust, up near the top where it says scientific community, we're held in fairly high regard compared to at the bottom, the press, the banks, the Congress, and the television people, and that we need to preserve that sort of ranking in terms of the public trust. And I think on the bottom line is as long as we continue doing good science, using the peer review system, I think that we'll be fine. Now, Steve Schneider, for many of you, he was a person who really tried to address on the communication issue and the media, how to deal with media and the policy. There are really many videos of Steve on the internet if you do YouTube, for example. But I want to show a very short one of Steve addressing in his own words on these subjects for the National Geographic News. It'll take a few seconds for it to get started here.
Scientist at Stanford University,
I hope the sound is
National
on.
Geographic Fellow,
Yeah.
and publisher of the new book Science as a Contact Sport. Dr. Schneider, can you tell us a little bit about your book and why you've written it at this point in time?
Well, thank you, David. So Science is a Contact Sport's already a pretty funny title. And the reason for that is for the almost 40 years I've been in this business, we were telling the Congress and ministers in Europe and all around the world about this problem in the 1970s. So the question I ask is, if we knew then pretty much what could happen and even how to fix it through energy efficiency and alternative energy systems and sharing arrangements with developing countries like China and India, why didn't we get the job done? And that takes a whole book to explain, and unfortunately some of the problems that we learned then are still going on. Comes down to really three basic things. Scientific community is honest, but not generally very articulate. And we tend to like things to be finished before we talk about them. So we wait for consensus, but by then it's too late to prevent some dangerous outcomes. So there's one reticence. Number two, there are special interests. People inside of industries that would be hurt by policies that increase price of energy, for example, and they're organized and they hire PhDs, literally hired guns, to sit there and say it's not true, and then the media, trained in political reporting, right, get the Democrat, get the Republican, fair and balanced in political reporting. But climate science isn't end of the world versus good for you. Those are the two lowest probabilities. So no wonder everybody's confused. They've got a complex issue that gets dumbed down to true or false when in fact it's a series of gradations with many serious outcomes, not every one of them, and it's complicated. So it's a problem that really challenges democracy. How can a democracy function when an issue is complex, yet people's understanding is critical to the political solutions?
Now, you've done a great job in the book of outlining the process and the debate over many years. And other than reading the book, which is obviously highly recommended, what would you tell people to do to get information they can rely on?
Well, I can never blame anybody for being confused when two PhDs are out there making opposite claims. So the first thing they have to try to do is find out what's a credible claim. Well, a generic. Watch out for the mythbusters and the truth tellers, the ones who have got the absolute answer of truth. When you hear somebody apologizing a little bit for the components we haven't figured out, talking in bell curves, saying that we shouldn't risk this because we're talking about the survival of the planetary life support system, not because we're sure, but we're buying insurance, they're much more likely to be telling you the truth than somebody who says, oh, no, it's not proved and it won't be proved for decades, or somebody else who says it's absolutely established, we must immediately stop it the day after tomorrow. So people can learn to do that. There are many good websites. The Environmental Protection Agency, the Department of Energy, the National Oceanic and Atmospheric Administration, NASA. There are many good university websites. There are European websites, even my own, climatechange.net. There are so many places where you can go to get the story straight. But when you do, it's not going to be in a soundbite. It isn't going to be, here's the truth. It's going to be, here are the range of outcomes, and why you as a citizen have to understand it well enough to know how you want to act to try to slow it down, both personally at home and politically at the national level.
Now, we're a few weeks away from the climate treaty talks in Copenhagen. What do you hope is going to happen, will be the outcome of that meeting, and what is likely to happen?
Copenhagen is when the world gets together to try to admit that the climate problem is the collective footprint of all kinds of individual, corporate, and national activities. So nobody can solve it alone because nobody created it alone. But we're not all equal. The U.S. is the largest historical emitter. China is now the largest individual emitter. So there are countries with a special responsibility. But everybody's got to be in the game. Therefore, we have got to replace the C word they teach us in business school, competition, with the C word we need to solve the planetary crisis, which is cooperation. So if you're a Chinese or an Indian, Brazilian, Mexican, you say, wait a minute, I only pollute 1/4 as much as you rich guys in the United States or Europe, so we'll catch up to you, then we'll take targets. But if you multiply that times they're having 4 times more people than we do, we have a planetary sustainability train wreck. We need to make a deal. We have to help them literally leapfrog over the Victorian Industrial Revolution with sweatshops and polluting industries like coal burning and internal combustion engines to high technology, to smart grids, to wind and solar, and maybe even smart nuclear, a wide range. Nothing should be completely off the table. But in order to fund that, we need cooperative deals, and Copenhagen at its best will structure cooperative deals. At its worst, we'll blame each other, point fingers, say the other guy's responsible, and go nowhere. I hope that doesn't happen, and with Obama as the president, I'm very hopeful that will not happen.
So you made the case for how we can deal with one another at a national level. To conclude, other than reading your book again, what do you advise individual people can do to make a contribution?
Yeah, one of the stories that I tell in Science to Contact Sport is when my students at Stanford said, but Professor Schneider, what can we do? We don't have any authorization to negotiate with the Chinese. Indeed. So I asked them, you turn your computer off when it's done? Well, sometimes I do and don't. That's important. Turn the lights out? Yeah. Are you consumers? Of course. Do you buy local produce? Well, sometimes. You know, local produce is a lot less embedded carbon. Do you guys, when you go out to buy a car, do you read the...
I think I'll stop it right now. I thank you very much for coming, and maybe I can answer a few questions if there are any.
So yes, please. Do we have some questions for Warren? Yes. Right.
Well, that's a good point, and yeah, I think that the poor models are getting better. Is why we see some improvement, but the good models still lack, in my opinion, certain things that we need from the observations. For example, we still don't have a good energy balance, all the way from the radiation going in and out of the planetary system, and also on the partitioning. So on the knowledge of the fluxes of either momentum, energy, or water vapor still are sort of unknown to us to a certain extent. We talk about the carbon cycle. Well, we don't have good measurements, globally, of the carbon cycle. So if you run these models where you use fluxes instead of concentrations, but you actually sort of allow the fluxes to change with season and time of day and so forth, we find that the models have sizable trends even for the period where we weren't increasing greenhouse gases. So I think observations are limiting ourselves to improving the models to pass a certain threshold.
Okay. Chuck?
Warren, I was very intrigued with that survey by the public of trust that scientists ranked third behind military and medical personnel. The number most interested me was the one on the far right that said don't know. I assume that means the surveyed person says, I don't know any scientists, so I don't know whether I can trust them or not.
Yeah.
Is that the way that should be interpreted? And why is it that the largest fraction of all the disciplines, why don't people know any scientists?
I don't know. But I think that the survey is one carried out every 4 years by the National Science Foundation Board. And it really tries to find out what a survey covers a whole bunch of things, but I find that this public trust issue is, I think, very important because we have a high degree of trust by the American public, and I think that we need to preserve that as much as possible. Even though people don't understand how science works and how peer review works and all those things, they seem to agree that we've made great progress, and especially in medicine, for example, the things that used to kill people now, many of them we have cures for, and medicine is really part of science, of course, and to have the public trust fairly high, I think, is important for us to not only get funding, but to actually get our opinions taken seriously in terms of public policy.
Thanks, Warren. I should have mentioned that Warren's wife, Mary, is in the front row here, so we should express our thanks to her as well. You had one more question right here? Yes?
So this is a comment. I was a postdoc at Steve Schneider's in the 80s. Steve was a great public communicator, but my field is in actually planetary science and astronomy. And in that field, we had Carl Sagan, now we have Neil deGrasse Tyson. We have these great public communicators. And I think that the climate change community really needs to cultivate and promote within its own community people to be great public communicators and to take on that role, because this is a critical issue affecting all of us.
I agree.
Yeah. Are there any others? One here, and then we'll
The RCP 8.5 is like way, way high and a lot higher than the next lower. Can you explain a little bit about what that is? The CO2 scenario slide.
RCP 8.5 basically assumes that we continue heavy fossil fuel burning. Even in that scenario, there's still a significant assumption of switching to alternative fuels, but it does assume we continue the pathway we're going right now, which is heavily using fossil fuels. Well, that's because they're going out over that time period. At 100 years, there's not that much difference between the different scenarios.
Yeah, I think the reason that we wanted to go out for 300 years was primarily to sort of look at the sea level change, because even if you cut emissions, you're going to be seeing on the sea level rising for a long, long time, even past the point of when on the temperature sort of levels off.
Okay, so let's thank Warren one more time. This afternoon we will have two other major presentations within global environmental change in this room. The next one will be the Tyndall Lecture. I see Ray Pierre Humbert's here. He's going to give that lecture. And then after that we have a new lecture series we're starting looking at kind of special hot topics every year. And Ken Caldera will be giving that lecture after Ray is finished. So please stick around if you can. I know there's plenty to do here at this meeting. I've been struggling with it myself, trying to go from session to session to session. But I think we have some really excellent speakers lined up. So thank you. We'll start again in about 7 minutes.